Suppose you have two qubits for evocative purposes. Suppose you're literally holding them as balls in your hands, one in the left hand and one in the right hand. The goal is to swap the qubits so that your right hand ends up holding a qubit storing the state of the qubit currently in your left hand and vice versa. How do you do it? Um, I like the picture. Where's the picture from? Okay, that's not very hard. Obviously, you can just physically move the qubits between your hands. Put one qubit down, pass the other qubit to the opposite hand, then pick out the qubit you put down. But what if they were glued to your hands? That sounds funny, but it's not intended as a joke. In practice, it's not always possible to physically move qubits. For example, your qubits might be etched onto a circuit board, hidden away inside a dilution refrigerator. You're going to have a bit of trouble moving those around. But then, but then this kind of seems to suggest there is nothing really else to it than just swapping. Like there's no interference um, trick to it. And maybe there's a way to do it. I don't know. Even if you can, or there's no intuition, no interference interpretation of swapping, or maybe there is, right? The same way you can do the XOR swapping, because that's another way you implement that. Um, okay. Even if you can, even if you can't literally physically swap the two qubits, it's still possible to swap their states, as long as you have the right operations available. For example, if I allow you to apply Hadamard gates, single qubit operation that rotates 180 degrees around the diagonal x plus z axis, transitioning the zero state to the 0 plus 1 state and the 1 state to the 0 minus 1 state, um, and controlled z gates to qubit interaction that negates the amplitude of the 1 1 state, then there is a series of operators you can do to swap the states of the qubits. We'll get to that specific case in a bit. The point is that in this post we're talking about swaps. We'll cover a few ways to do swaps, how to generalize swaps, and how to specialize swaps. Okay. One of my favorite websites is Beat Twiddling Hacks. It's a bunch of low-level programming tricks for computing simple functions in few operations, and it's fantastic. For example, you need to count the number of 1 bits in a 32-bit register. It's possible to do so in 12 operations, and that site will show you how. Interesting. One of the bit twiddling tasks on the side is swap two variables without using any extra space for a temporary variable. That is to say, rewrite the following code so that it operates only on A and B without using a temporary T. Using a language, okay, that's some kind of solution. One solution to this problem covered by the bit twiddling hack is called the XOR swapping. Um, you just XOR assign the two variables back and forth and back, and they ended up swapped. To really see why this works, I recommend doing a few examples by hand. For our purposes in this pause, the interesting thing about XOR swapping is that it only uses reversible operations, which means it will work on qubits. The statement A XOR equals B means for each bit position, if the bit in that position in B is on, then toggle that bit in A. There is a quantum equivalent of this if B then toggle A operation, the controlled NOT. Thanks to the control NOT, we can implement the XOR swap on a quantum computer. All we need to do is chain 3 C knots back and forth. So let's go through the 4 basic states to see how this works. So where's twiddling hacks? Oh yeah, there's a bunch of stuff in here. It's interesting. Swapping values with X or. Mhm. That's interesting. Uh, 0, 0, desired output is 0, 0. The first C naught control is not satisfied, we stay in the state 0, 0. The middle C naught is not satisfied, we stay in 0, 0. The final C naught control is not satisfied, we stay in 0, 0. Correct. Desired output is so 0, 1, you want 1, 0. The first C naught is not satisfied, we stay in 1, 0. The middle C naught is satisfied, the bottom qubit gets toggled, the transition to the state 1, 1. The final C naught control is satisfying, the top qubit gets to 1, 0 here. Correct. Same happens here, and here is sort of the same like in, obviously it's not the same, but it's, so they stay unchanged, but they change in between, right? So the first is satisfied, so you get to 1, 0. The second is not satisfied, so you get to stay 1, 0, and then uh, and then the other one is satisfied, so you go back to 1, 1. Okay. So all 4 classical cases work, but what about the quantum cases? The qubits could be superposition, entangled with other qubits, entangled. Yeah, that's the thing. You say entangled with other qubits. No, entangled with each other. Okay. So all 4. Okay. For example, this state is unaffected by NOT gates. Couldn't initializing the bottom qubit to that state prevent the first C naught from achieving this purpose, thereby running the swap? Couldn't initializing the bottom uh, what will be the bottom qubit, you mean? The short answer to this word is the rule of thumb. Quantum mechanics is linear, so if it works in the basis states, then it works for every state. There are exceptions to this rule, but only for circuits involving extra work qubits. Example, the phase kickback used in Shor's algorithm. Our circuit has no extra qubits, so we're fine. I still don't get it what he means by initializing the bottom qubit to that state. Couldn't initializing the bottom qubit to that state prevent? Does he mean, because this is 1 qubit, right? Uh, anyways, XOR swapping with Harmards and control Zs. We now know how to swap 2 qubits by applying CNOT gates to them. If we don't have CNOT gates available as the basic gate set, then we can still use this strategy. We just need to build the CNOTs out of available gates. For example, the gate set control Z plus Hadamard doesn't include a CNOT, but you can still, you can build the equivalents. So you do that. The effect is a CNOT with a Hadamard framed qubit as a target. Why does this work? It has to do with the reason that in quantum computing we call the NOT gate X and the phase flip gate Z. The Hadamard operation is a 180-degree rotation around the X plus Z axis of the Bloch sphere. If you have a state along the X axis of the Bloch sphere, example X on, the Hadamard operation will rotate that state along the Z axis to Z on. Analogously, the Hadamard will rotate the Z-axis states into the X-axis. For this reason, framing an operation with Hadamards converts any interactions along the z-axis into interactions along the x-axis and vice versa. The not um, gate is an x-axis interaction. The face flip is a z-axis interaction. So the Harmar operations turn one into the other. Now, for more discussion on of these not as X interaction stuff, see the post thinking of operations as controls. Yeah, that was definitely a good post. But I'll cover a bit here. Basically, CZ gate, control Z gate can be thought of as meaning when qubit C is Z on, negate the amplitude of the Z on state of qubit T. And that same language, the C now means when the qubit C is Z on, negate the amplitude of the X on state of the qubit T. Or by speaking at the level of the whole system, we can say that the control Z gate means negate the amplitude of the control Z means the whole system, control Z negate the amplitude of the Z on state. Whereas the C naught gate means negate the amplitude. I never thought of it this way. Huh. Negate. I never thought of it this way. That's the way you think about it at the system level, and so that's also the way you think um, about a C naught at the system level. Negate the amplitude of the Z on X on combination. Interesting. So of that particular superposition, 1, 0, minus 1, 1. Now you always learn something. That's interesting, definitely. So you see, that's quite interesting when you try to think about those operations at the system level. This is why that's why framing one qubit of a CZ would Hadamard turn the CZ into a C naught. Now let's think about axes besides X and Z. The C naught operation negates the amplitude of the state Z on X on and leaves perpendicular states alone. C naught negates the amplitude of the state. What are perpendicular states? Perpendicular states to what? To these? Negates the amplitude of the state Z on X on. As suggestive shorthand, I'm going to write the C naught operation as the expression C naught 1 2 equals Z1 X2. Okay. The tilde is notation I just made up for this post. It means combined in the way that makes one control the other. I'll be referring to the operation performed by the tilde operator as the control product. To be mathematically precise, I define the control product of two commuting unitary operators A and B. What? To be X minus what? Side note for physicists. Yes, I'm just multiplying the Hamiltonians together. Okay. I don't know how can then this be useful later on, but let's take a look. Interestingly, even though we started with an asymmetric concept, one operation controlling another, the math ended up symmetric. You can think of either operation as being the control of the other. Correct, but that's if you think of it at the system level, exactly. So basically that would mean turn Mm. Uh, can you think of it this way from a control node perspective? It's not. Negate the amplitude of this. Okay, I'm not entirely sure I can apply the same view to the control node though. But this is more of a generalization, what he's trying to do here. We can sanity check the control product definition by verifying that the control node operations matrix is in fact the control product of phase flipping the control and toggling the target. So this is the X matrix and this is the Z matrix. Control product, return these. So basically this is the indeed the control node matrix. So wait a second, so you're just multiplying, no. You're just multiplying the Hamiltonians, that's what you're saying here? Just multiplying the Hamiltonians together. Of X and Z. I kind of see what he's doing, but I don't see where he's going with that. So let's go. That's the matrix of a C node. Yeah, yeah. Now let's write our XOR swapping algorithm down, but in the language of the control product. It's pretty simple. The operations that XOR swapping applies are Z1 X2, X1 Z2, Z1 X2. Notice the alternating back and forth pattern. That's it. To be safe, we should check that multiplying those operations together returns the correct matrix. Yeah, that's the matrix of the swap. I'm a bit like I'm going slow because I think I'm not gonna rush this because this he's definitely trying to go somewhere. Yeah, that's the swap matrix. A natural question to ask here is what happens if we use this alternating pattern on other axes of the qubit? Is XOR swapping specific to the X and the Z axis, or does it work more generally? Well, clearly it can be specific to those axes. The fact that we call one particular axis the Z-axis or the computational basis is just an arbitrary convention, a coordinate system. The underlying math is independent of our naming convention, so this alternating technique must work in some sense, no matter which axis we use. Just to be sure, we can test in Python if we're using the X and the Y instead of the Z and the X works. Swap X, Y. Uh, the X and the Y. Wait a second, what does it mean to swap the X and the Y then? It's not your... Wait a second. Just to be sure we can test them out. Yeah, so that's the matrix of the swap. In which has support for X-axis and Y-axis controls. That's pretty cool, by the way. No! Here. So what's going on here? So this animation is doing an X rotation, and then so you're doing a swap, but you're doing it through another set of axes. So you're using an X control. So if I replace these with Z gates, we should see the same effect. That's an interesting effect when you have that. Okay. Yeah, exactly. Interesting. Oh, okay. Yeah, so basically that's those three things equal. Okay. Based on this quick test, it would be reasonable to conclude that the alternating control product interactions trick will perform a swap regardless of which axis pair we pick. However, there are some exceptions. In particular, if we pick two axes that aren't perpendicular to each other, x, for example, x on diagonal x plus z, then the swap doesn't work correctly. The reason we need to use perpendicular axes comes down to the fact that the observables of those axes anti-commute. In some fundamental sense that I'm not going to try to explain, pairing the x-axis with the z-axis works because their axis flip operators have an anti-commutator that satisfies... what is an anti-commutator? By using the commutator... In mathematics, the commutator gives an indication of the extent to which a certain binary operation fails to be commutative. These are different operations. Okay, group theory and ring theory. The commutator of two elements G and H of a group G is the element GH, and is equal to the group's identity if and only if G and H commute. By commute meaning that G times H is the same as H times G, so that their effects are independent of the order. So he's saying is in the anti-commute the anti-commutator of two elements A and B of a ring is defined by AB plus BA. Sometimes commutator, anti-commutator. Sometimes it is used to denote anti-commutator. The anti-commutator is used less often, but can be used to define Clifford algebras, Jordan algebras. The commutator of two operators acting on a Hilbert space is a central concept in quantum mechanics, since it quantifies how well the two observables described by these operators can be measured simultaneously. The uncertain principle is ultimately a theorem about such commutators by virtue of the Robertson-Schrodinger's equation relation. In phase space equivalent commutators of function star products are called Moyal brackets and are completely isomorphic to the Hilbert. So what does it mean that it anti-commutates? Anti-commutativity. In mathematics, anti-commutativity is a specific property of some non-commutative operations. In mathematics, where symmetry is of central importance, these operations are mostly called anti-symmetric operations. They are extended as and are extended in an associative setting to cover more than two argument swapping. Definition: an n-ary operation is anti-symmetric if swapping the order of any two arguments negates the result. Okay. So basically what this means is that it anti-commutes. It's, you can see this in the matrix. No, yeah, that it anti-commutes. It means that xz equals to minus zx. So it kind of commutes, but negating the result. And so, and what Craig is saying is that's the reason why the swap works, only because those two observables. Interesting. Generally speaking, if the axis flip operators A and B satisfy these, then and the anti-commutator is just a mathematical construct that tells you how well something anti-commutes or not. So if it's 0, it means it anti-commutes. Then the operation axis swap ABIJ is a swap operation between the qubit I and qubit J. We've generalized from XOR swapping with C-naughts to a construction that can swap two qubits by back and forth interacting two qubits along any perpendicular pair of axes, but we're not done generalizing yet. Okay. I don't know if I should let that sink in for a while. I think I'm gonna let that sink in for a while. It's this is pretty. I didn't expect that to go that way. So far, I'm kind of like done with half the post, I would say. And this is a really interesting learning. That you can swap using any pair of axes, really. Any pair of perpendicular axes. So, x and y, x and z. Yeah, interesting. That's definitely interesting. These and seeing the C-naught operation as negating the amplitude of the z on x on state. So the state 1 minus, which is this. Interesting. I feel like I gotta get a bit more in shape with superpositions and interference, because especially also after what I discovered from Grover's algorithm, it seems that that's the essence of a quantum algorithm. It's like manipulating the interference, manipulating the superpositions and creating the interference. And I think that's there's no more like woo-woo to that, you know what I mean? Like, it's weird because it feels low level, but it doesn't feel low level, you know? Okay. So I'll leave it here for now. I'll let that sink in for a little bit. Then I'll do another video with the rest of the article, which is generalizing axis swapping into observable swapping. That can be interesting. Some animations. X, Y, Z swapping. Okay. Specializing the X, Y, Z swap. Far swap. And summary. Interesting. Cool. Perfect. That was definitely more interesting than expected so far.